Welcome back. This is section 2.5, linear functions and models. So in this section, what we're going to look at is what first is a linear function, and then how can we actually use linear functions to actually model real world situations and actually solve problems. All right, so first off, a linear function is any function that can be written in the form f of x equals mx plus b. So if you recall back to chapter 1, right, we've already talked about linear equations. Now we're just saying that linear equations are indeed functions because they pass that vertical line test. Every x value has exactly one y value associated with it. And so now we can define these linear equations as linear functions. Okay, so again, recall m is going to be our slope, and then the b is going to be the y-intercept. Okay, and so this would be slope-intercept form of a linear function now. All right, so example 1 here, we want to determine whether the given functions are linear, and if it is linear, we want to put it in that mx plus b form. Okay, so we take a look at the first one here. We've got f of x equals 2 plus 3x. So the question is, can we somehow rewrite this one to get it into mx plus b form? Well, if I just rearrange my terms here, because remember addition is commutative, I can switch the order. That's going to give us 3x plus 2. And now you can see that we have this in mx plus b form, where 3 is the m value, 2 is the b value. And so this would be a linear function. Okay. All right, let's look at g of x. Okay, so again, we're trying to see, is there anything we could do to get this in that mx plus b form? So the first thing I'm going to do here is I'm going to distribute my 3. And if we do that, that's going to give us 3 minus 6x. And then again, if you want to actually get this in mx plus b form in the correct order, then we can actually rearrange our terms here, keep the negative with the 6, so we have negative 6x. The 3 was positive, so that's a plus 3. And again, we have mx plus b, where negative 6 is our m, 3 is our b. And so this, again, would be a linear function. So I'm going to do the same thing on the next one. I'm going to distribute first just to see what happens. If we do that this time, we're going to end up with a 4x, and then x times 3x would be plus 3x squared. Now, looking at this one now, I have an x squared term, which automatically tells me that this is not going to be a linear function because I'm not going to be able to get it in mx plus b form. Okay, so whenever you have an x squared, it's automatically not linear. So this one right here, we would say is not linear. All right, and then the last one here, the first thing I'm actually going to do is I'm going to simplify what we've got here. And so I can actually take each of my terms and divide them by 4. And if I do that, that's going to give us 1 over 4 minus 5 over 4 times x. All right, and notice here we do just have an x to the first power. And if I just rearrange my terms now, we would have negative 5 over 4 times x plus 1/4. And in this case, the negative 5/4 gives us the m value. The 1/4 gives us the b value. And so this is actually a linear function. So a couple of these, up front don't necessarily look like they would be linear, but by simplifying first and rearranging terms to get them in that mx plus b form, we can show that these are actually linear functions. Okay, and so the only one that's not here is the third one where we get the x squared. Okay, that would not be a linear function. All right, slopes and rates of change. Okay, so for the linear function f of x equals mx plus b, the slope of the graph of f and the rate of change of f are both m. Okay, so in other words, the terms slope and rate of change are interchangeable. Okay, so if I say rate of change, I'm referring to the slope. And if I talk about slope, I'm referring to the rate of change, right? Those two things mean the same thing. Okay, and in both cases, they're the m value of your mx plus b form, which is just the coefficient of your x term. All right, so example 3. We have a dam built on a river to create a reservoir. The water level f of t in that reservoir at time t is given by the function f of t equals 4.5t plus 28. T is going to represent a number of years since the dam was constructed. F of t is going to represent the height of the water level, and it's going to be measured in feet. Okay, so t is the number of years since we built the dam. F of t is the height of the water measured in feet. Now, the first thing they tell us here is to sketch the graph of F. So what I'm going to do is I'm going to put this in Desmos, and we'll look at it together. And then we'll start to talk about what we know about this graph and what those things actually tell us. So in Desmos now, I'm going to write this as f of x, even though it's an f of t. So f of x equals 4.5x plus 28. Now notice in this case, right, we can't see a lot of the key information because remember our x-axis or our t-axis in this case is going to represent an amount of time. So we probably mostly care about positive values since we're looking at a number of years since we built the dam. So I'm just going to go ahead and first slide this over and say, well, I pretty much only care about positives, so I'm going to focus on this area over here. Now I can't see any of my graph, so that tells me automatically I need to adjust my y-axis so I can see what I really care about, right? Well, we know the y-intercept this time is 28, and we know our slope is positive, which means I want to at least go to 28 and above, right? So I'm going to go ahead and just adjust my y-axis here. I'm going to adjust my y maximum to be about 50, right? Just so I know I can at least see part of my graph. So we can come over here now. If you click on your line, you can actually click on the y-intercept, and so we can see there it does cross at 28, right? That's the height of the water level at our starting time when the dam was first built. And then we can actually see as time goes on what's happening to the water level. Now, the first question that was asked here, right, and I'll go back to the slides so we can kind of talk about this together in a minute, but while I've got the graph up here, first question was, what is the slope? Well, in this case, remember, the slope is just going to be the m value of your equation, which is 4.5. Okay, so we have a slope of 4.5. And again, recall, slope and rate of change are the same thing, right? So what that slope represents now is a rate of change of our function, and the function represents a water level. So now the next question is, at what rate is the water level in that reservoir changing? Well, we know it's 4.5, so now we just have to think about, in the context of the problem, what does that actually mean? Well, our f of t is the height of the water, the t is the amount of time in years, and so we can say in this case that our water level is rising because it's going up, it's a positive value, at a rate of 4.5 and in this case that would represent feet per year. So every year that we go, we're increasing our height of our water level by 4.5 feet. All right, so I'm going to go back to my slides now. Right, so you can see in this case, the slope of our graph, we said that's just 4.5, right? Because the slope is just a number, right? It doesn't really represent anything in the context. But then when we asked about the rate at which the water level is rising or changing, we would say that it's now rising at a rate of 4.5 feet per year because of the fact that it's a positive slope, a positive rate of change, and our units here were in feet for the water level and years for the amount of time. Now, if our slope had been negative instead, then just keep in mind that we would say that our water level would be falling at that rate, because a negative slope in that case would mean that the water level is going down instead of up. All right, example 4. So now we've got water being pumped into a swimming pool at a rate of 5 gallons per minute. Initially, the pool contains 200 gallons of water. So we want to find a linear function, we're going to call it v, that models the volume of water in the pool at any time t. So first off, I know my function here is going to be v of t, where v of t represents the volume of water in the pool at any given time. Now we have to go back to the word problem and figure out, well, what information are we given? Okay, so I notice here that I have this word initially. Anytime we see that word, that just means that's our starting value. Well, a starting value in terms of a linear function is the y-intercept. So basically, this value right here now gives me the b value for my equation, the y-intercept. Now I'm going to look for other keywords, and I see the word rate. And if you remember, I told you before, the rate of change of a function is just the slope. And so because I have a rate this time of 5 gallons per minute, that actually gives us the slope of our equation. So those two values that are given actually give us the m and the b for our mx plus b. So now I'm just going to substitute them in. And so this is going to be 5 times t, because we're using t as our variable this time, and then plus 200. Okay, so this linear equation now tells us we have a starting value of 200 gallons, and we are rising at a rate of 5 gallons per minute. All right, now once we have that function, the next question is, if the pool has a capacity of 600 gallons, how long would it take to completely fill the pool? So all we have to do now is think, well, 600 represents a volume, a number of gallons. I'm going to substitute that in place of my volume in my linear equation, and I'm going to solve for t since I want to know how long. So I'm going to say 600 is equal to 5t plus 200. And so again, as soon as I see the words how long, that tells me I'm looking for a t value. And in this case, we have a capacity of 600 gallons. That tells me the volume of my pool now. Now we just have to solve, right? So I'm going to start by subtracting the 200 from both sides. That's going to give us 400 equals 5t. And then we just need to divide both sides by 5. And so if I do that, that should give us 80 equals t. And now with all of these context problems, we always want to think about what units we might be dealing with. So recall here, we found a t value. Our time in this case was going to be measured in minutes. And so this is 80 minutes to completely fill that pool. All right, example 5. So we have a figure here that's given, right? That's the picture down in the bottom. We have placed a staircase in a coordinate plane. With the origin at the bottom left corner, the red line in the figure is the edge of the trim board of the staircase. So we want to first find a linear function h that models the height of the trim board above the floor. So we're basically just trying to figure out what is the linear function that would model that red line, and that red line represents the trim board. So in this case, we're going to use h. And then notice here, they actually gave us x as the variable on that axis. So I'm going to call this h of x. And so the things I need now are the slope, and I need the y-intercept. Well, the y-intercept here, we can see from the graph, it's that starting point. And so 8 is actually going to be the b value, right? Because that's where it crosses the y-axis. Now I need slope. Well, I could count, right? That's one way to kind of do this, but our scale is a little wonky, right? So it might be hard to kind of count what's actually happening for rise over run. But I am given 2 distinct points, and I can use my slope formula to calculate the slope from those. So that's what I'm going to do up here. Remember, our slope formula is going to be y2 minus y1 over x2 minus x1. So I have an x1, y1 value here, an x2 and y2 value here. I'm going to start with 32 minus 16 over, and then x2 minus x1 is going to give us 36 minus 12. So now we just need to simplify that. So 32 minus 16 is 16. 36 minus 12 should give us 24. And now we always want to simplify. In this case, 8 actually goes into both of those values. So 16 divided by 8 would be 2. 24 divided by 8 would be 3. And so now we have our slope, which is going to be 2/3. So now that we have our slope and we have our y-intercept, now we can write our function. This is going to be 2/3 x plus 8. All right, so that answers the first part. Now the second part says if the space available to build a staircase is 11 feet wide, how high does the staircase reach? So what we want to figure out now is what is our h of x value if the staircase is 11 feet wide, meaning the x value here is going to be 11 feet. Now be careful. Notice this time that our x-axis has inches as its units. We're given a width of 11 feet. So the first thing we've got to do is actually convert that 11 feet over to inches before we can substitute it into our function. I'm going to take 11 feet. I'm going to do my conversion. Now, when I do conversions, I always multiply, and I'm going to multiply by whatever the conversion factor is, trying to cancel out the units that I want to get rid of and end up with the units that I want in my answer. Okay, so I know I want to end up with inches, so I'm going to put those in the numerator. And I know I need to cancel out feet, so I'm going to put those in the denominator. Now I'm going to think about the conversion between feet and inches. Well, for every 1 foot, we're going to have 12 inches. So there's my conversion. In this case, my feet now cancel out because I have feet on top and bottom. And when I multiply this now, I'm going to have 11 times 12, which should give us 132 inches. Now that I know how many inches I'm dealing with, now I can substitute that into my function. So we're going to take h of 132, which is going to give us 2/3 times 132 plus 8. And at that point, we can just go straight to our calculator, multiply 2/3 times 132, add the 8, and when we do that, that should give us 96. Now we found an h of x value or a y value. Notice here that that's measured in inches also. So this is going to be 96 inches. Now that answer is perfectly fine, but if for some reason you wanted to take this back into feet, since the original units were feet, right, 11 feet was given, we could convert this inches back into feet now. So I can take 96 inches. Again, I'm going to multiply. This time I want to cancel out inches, so I'm going to put those on the bottom. I want to end up with feet, so I'm going to put that on top. And again, we know for every 1 foot, we're going to have 12 inches. This time my inches would cancel out. I would end up with 96 over 12 feet. And when we simplify that now, 96 divided by 12, that should give us 8. And so 8 feet would be my answer. Okay, so again, 96 inches is not wrong, right? But if you did need it in feet instead, then we can just convert back into feet from inches. So this tells us if our staircase was 11 feet wide or deep, might be a better way to kind of think about this, okay, then it would rise 8 feet. All right, example 6. So John and Mary are driving westward along I-76 at constant speeds. We've got our graph down here in figure 5, shows the distance y in miles that they have traveled from Philadelphia at time x, which is going to be measured in hours, where x equals 0 corresponds to noon. So note here that at noon, John has already traveled 150 miles because John's starting position at noon is 150. And Mary has not started yet, right? She is starting at noon and then driving from there. All right, so our first question here is, at what speeds are John and Mary traveling? So the way we're going to determine speed in this case, if we think about it, down here we have times, right? So our x-axis represents an amount of time, and then our y-axis represents distance. Well, if I want to know a speed, speed in this case is going to be distance over time. And so if you think about, speed in a car typically would be measured in miles per hour, miles being a distance, hours being a time, and so our speed is going to be a distance over a time. Well, a distance over a time in this case is just going to be a rise over a run, which is the same thing as calculating a rate of change or a slope. So all we really need to find their speeds is the slope of each one of those lines. Okay, so I'm going to start with John here, and I'm going to find the slope of John's line. So for John, m is going to equal, and again, we need points to be able to calculate the slope. So I'm going to look at our points that are kind of labeled here. This point up here now looks like it's going to be at 4 and 350. And then our point down here looks like 250. So I'm going to use those points now. So again, it's going to be y2, so 350, minus y1, 250, over x2 minus x1, 4 minus 2. And now if we simplify that, that's going to give us 100 over 2, or 50. Now, we need to keep in mind what our units are. Okay, so if you recall, these times down here now represent hours because 0 is noon, 1 would be 1 p.m., 2 would be 2 p.m., and so on. So this is going to be a time measured in hours. And then our distance up here from the last slide, they told us was going to be measured in miles. And so that 50 that we get there now is going to be a distance per time, or in this case, a miles per hour. And so John's speed is 50 miles per hour. All right, now let's look at Mary. So again, I want to calculate slope, so I'm going to need 2 points. So I'm going to find points on Mary's graph. So this is going to be 4, 300. And this other point is going to be 2, 150. Again, substituting into our slope formula, we're going to start with 300. We're going to subtract 150. And we're going to put that over 4 minus 2. This time, 300 minus 150 is going to give us 150 over 2, or 75. And again, those units are also going to be in miles per hour. So John's traveling at 50 miles per hour. Mary's traveling at 75 miles per hour. Right, now, the second part of that question is, who's traveling faster? Well, Mary is traveling faster, right? And then how does that show up in the graph? Well, if we look at our graph here, notice that Mary's line, the blue line, is actually steeper than John's line. And so Mary's rate of change is higher, faster, than what John's is. Okay, so we can actually just look at the graph in this case and tell that Mary is traveling at a faster rate of speed because her slope is steeper than John's. All right, now the next piece here is we want to find functions to model the distances that John and Mary have traveled as functions of x. Okay, so we'll start with John. Well, the speed that we found is the rate of change or the slope for John, right? So we already have the m value, and then we can just look at the graph to determine the b value, and we can write our function. So in this case, I'm going to call this d of x, right? Since we're saying that our y value is going to represent a distance. And we're going to start with the slope. So that's going to be 50 times x. And then we're going to add the y-intercept. In this case, John's y-intercept right here on our graph is going to be 150. And that makes sense because if you recall in the previous slide, we said that John starts 150 miles from the starting location, right, at noon. So he's already 150 miles away. All right, now if we look at Mary, her equation, we're going to have 75 as her slope. And notice her y-intercept this time is 0. And so we actually don't need anything else there, right? So plus 0 wouldn't change anything. And so we can just call her distance function 75x. All right, now the next question says, how far will John and Mary have traveled at 5 p.m.? So let's start with John. Remember, noon represents 0 in this case, so 5 p.m. would just be a value of an x value of 5. So all we really want to do here is substitute 5 into our function. So we're going to have 50 times 5 plus 150. And if we multiply that now, 50 times 5 should give us 250 plus 150. So that tells us that John has traveled 400. And again, this d of x is representative of a distance, and our distance in this case is measured in miles. So John has traveled 400 miles. And now for Mary, again, we're using our distance function for Mary this time. D of 5 is equal to 75 times 5. And if we multiply that this time, that should give us 375 miles. So at 5 p.m., it looks like John has traveled 400 miles, Mary has traveled 375 miles. All right, and then the last piece of this says, for what time period is Mary behind John? And then will Mary overtake John, and if so, at what time? Okay, so basically what we're trying to figure out is, we know that Mary's traveling faster. We know that at some point she should catch up, and we want to figure out when does that happen. So the way we're going to figure that out now is we're actually going to take the distance for John and the distance for Mary, and we're just going to set them equal to each other, right? Because if I want to know when they catch each other, when Mary catches John, we need their distances to be the same. So I'm going to set their distance functions equal. So I'm going to set 50x plus 150 equal to 75x. So that's basically saying, when is John's distance equal to Mary's distance? Now to get x by itself here, I'm going to subtract the 50x and move it to the other side. So we'll have 150 is equal to 25x. And then we just need to divide both sides by 25. And if we do that, that's going to give us 6 equals x. And again, keep in mind in this case, the x represents a time, which is a number of hours. So this says 6 hours. Okay. Or if you actually want the time, we know our starting time was noon, and so 6 hours after that would be 6 o'clock p.m. when Mary overtakes John. And so for every time between noon and 6, John has traveled further, and any time after 6 p.m., then Mary would have traveled further. And at 6 p.m. exactly, they would have traveled the exact same distance at that point. All right, so that's all there is for that section now. As always, let me know if you have any questions about anything. Send me those questions in WebAssign using the Ask My Teacher button if you need to. Drop in during my student hours whenever you need, and I will see you next time.